on this? Or is that not possible through Discord? Oh, okay. Okay, cool, cool. Okay, awesome. Okay, thanks, guys. All right, so then recording should be okay. Okay, then thank you again for your patience. This is really annoying to figure out all of the different tech stuff as well. I'm usually used to like Zooms or like Microsoft Teams. Maybe we can do that next time. But yeah, thank you guys for tuning in. So as you guys know, today I'll be covering just electromagnetism just in general. You guys obviously know a bit about me already from the stuff that I've entered into the chat. So I'm a Sukada and I graduated in 2021. And I'll be hosting your physics masterclass today. And specifically, we'll be covering like, electromagnetism in general. So the one thing that I do want to mention though in the under the electromagnetism thing is that I will basically, in terms of the syllabus points, I won't go through the electrostatics part just because when I was looking through that, I think that was somewhat relatively easier than the magnetism parts of it. So like for example, like Coulomb's law and like what actual like electric field strength, electric potential energy, all of that it seems pretty straightforward. So I'm just gonna there is a few things that I'm gonna cover under like electrostatics overall because it's important to magnetism, but I'm not gonna cover the syllabus points about that. And the other thing to know about syllabus points as well, I'm going to cover all of the syllabus points under electromagnetism except for the solve problems one. And this one is just because, and it for some of you it might be a bit annoying because like you might be coming here to do the solving problems part. However, this is the biggest thing for me for physics, and the reason why I think that personally attributed to like my physics score, I think, is that I didn't focus on like solving problems, if that makes sense. I didn't focus on the formulas and solving problems and solving questions. It was rather understanding the theory and relating it to like the real life applications and stuff like that. And then the solving problems, yeah, exactly. Conceptual understanding. That's exactly correct. Yeah. So um I didn't like, and then kind of the solving problems came after it because when you guys understand the theory behind it, then you'll understand the formula and how to apply the formula. That's just easy. That's just maths, right? I'm sure most of you guys here today who do physics are probably doing methods, if not even specialist maths. So it'll be pretty easy, the formula substitution part. So the theory is what's important. In terms of like the highlights as well, don't listen to that much about that. Most of it is relevant. So just I think just learn everything basically that I'll be saying today, basically. The other thing is again, apologies for the lack of aesthetics in the PowerPoint. I just like honestly just put some images in there, so nothing like the other masterclass you might have come into. So but yes, apart from that, I'm happy to start now. So the first thing that I'm gonna go through is quickly the slider thing. So if you guys want to do the like slider thing, just take a QR code or just go to slider.com and then put that like number in, and then you guys can just enter questions and it's completely anonymous as far as I know as well. So you could literally ask what is physics as well. So like my brother asked in the chat as well. So um yeah, you could ask that as well. And in the meantime, while you guys doing it, what is physics? That's a good question. So, um, physics. So the word I when I learn a word physics, it's I generally get the prefix or the suffix of it. So the prefix of physics is phys, and that just means like the world, the universe in general, right? So it's kind of like the understanding of like the world basically, which is like probably the best subject in my case, right? There is a subject that I do in medicine now called physiology, and it also has that phys word in it too, which is interesting, which is like why I like looked up the comparison as well. Physics is obviously more of the workings and the functional kind of aspects of the world, whereas physiology is kind of like the processes, specific processes, biological processes that work in the world. So that's like the difference if you guys are planning on to doing medicine or anything. So um yes, okay, awesome. I think that should be enough time for you guys to do that. So let's get right into it. Okay, so let's start simple, really simple. Let's just go with defining the term magnetic field. All right. So pretty straightforward, right? Magnetic field, it's just as it says, it's a region around any magnetic like material or moving electric charge where magnetic fluxes are experienced. So primarily two things are permanent magnets. So the one that you see there, but bar magnet is obviously the classic example of a magnet that we see, the horseshoe magnets, those things. But obviously the biggest one that we know of is the Earth's magnetic poles, the geographic poles as well. So this is obviously how compasses works, and that actual that specific compass reference I will bring up later as well. But that is essentially the larger kind of more. Oh, thank you also for putting that slider thing in. Awesome. Um, so yeah, that's like the larger kind of magnetic poles that we know of as well. So as it says there, this is a very important concept. So what is magnetic fields produced by generally in the world? So we've got the two things, magnetic materials, right? So what I've just mentioned, the permanent magnets and then the Earth's magnets. And then we've got moving electric charges. And this is a classic, this is basically the whole kind of topic of today, right? Moving electric charges creates magnetic field. Sorry, I just saw a question. So charge moves from north to south pole. Yes, yeah, I mean like that's yeah, so for any magnet, solenoid, permanent magnet, and as you can see here in like the Earth's like geographic, that's yes, that is correct. Okay, so next thing that's important in terms of magnetic fields is obviously the strength and the direction of magnetic fields. So this is kind of like basically more relevant to magnetic field lines itself. So whenever we draw magnetic fields, so you can see here in the specifically in the bar magnet, it's you've got the first one and you've got the second one, right? So in this case, the distance between each magnetic line determines the strength of it, right? And obviously the direction is just the arrows, right? But I'll talk a bit more about this in the next slide. There we go. So the properties of magnetic field. So we've got directions. So that's when, as the person said in the chat, so it was basically from north to south pole. That's how magnetic fields are, obviously. Density. This is essentially equivalent to the strength. And we'll talk about this more later on in the magnetism part, the induction section. But strength, magnetic field strength is basically the magnetic field like density. What does density mean? So density is basically the number of like say lines per unit area, right? So that's in physics, that's what density means. Obviously in chemistry it means something else. It means grams per volume or something like that, right? But in here it's the number of lines per area, right? So the closer the lines are, so if you have closer lines together, right, that means you have more lines per unit area, therefore higher density, therefore higher strength of magnetic field. So obviously, why is this important? Why do we even care about like magnetic field strength, magnetic density? It is incredibly important when we talk about electromagnetic induction later on and transformers. So this is really important when there's a fluctuation of this density. So when we have changes in density, that's essentially how we induce currents. Like, again, I don't want to bring things later on now, but that's why it's so important. So keep this in mind. The closer the lines, the stronger the magnetic field. All right, cool. Um, yeah, as we mentioned a lot of times, biomagnets, any magnet really goes from north to south. So current carrying wire. So this is a very important thing. So when you have an electric charge, so I think I might just talk about this in the next one. Okay, yeah. So this is the phenomenon that's very, very important. So this is basically how the first person, that's the Ørsted guy, so Hans Christian Ørsted, that's in your textbook. If you guys use the Oxford textbook. It's basically where, so you have an electric charge, right? We know what does an electric charge do? So stationary static electric charge, we know it releases what? It releases an electric field, right? So just like a magnet releases a magnetic field, you have an electric charge that releases an electric field. And obviously we know this by Coulomb's law. Coulomb's law is the one who basically, it's like basically a copy of the Newton's law of gravitation, universal gravitation, right? It's basically where we see two charges interacting with each other. The Coulomb was the main guy, obviously, that like talked about electric charges. The chat. Oh yeah. So do we get this PowerPoint? Yeah. Honestly, I'm happy to send this PowerPoint in. I'll send the PowerPoint in. Yeah, I guess in the Masterclass updates channel afterwards. So yeah, that's all good. Yeah. I'm assuming this is also, if this is getting recorded, I've seen them get recorded, like sent to like YouTube as well. So you guys have like access there as well. So I'm assuming. Um, but yeah, awesome. I'll keep that in mind to send that after the class as well. Okay. So yeah, so stationary charge creates an electric field. That's pretty straightforward, right? Um, so the thing is, what happens when you move that charge? That's the biggest thing. So what happened was this Ørsted guy, right? He was basically giving a like a lecture, like a class on electric fields because he was pretty like, this was his field. And he was actually technically his overarching research as well. Like he was like this is not when I say it's an accidental experiment, it's not really accidental because he was researching this over his entire lifetime, basically. But while he was teaching a class, he had a wire connected to a battery. So he was just talking about like, to his class the wire connected to battery, and he just happened to have a compass nearby. So as soon as he turned the current on that like in the circuit, that compass needle like started moving. And this was basically the first ever experiment on the like relationship between electricity and magnetism, right? And it's basically the relationship he like established that relationship between electric currents and magnetic fields. That was like the key kind of like turning point. And obviously this like this at this point Faraday, Maxwell, all of these guys were also kind of like researching this as well, so that everything that they did arguably which were more important were based on this guy Ørsted's like I guess foundational kind of basic knowledge here. So yeah, so that kind of created that electricity and magnetism thing. So that's when he realized essentially electricity, somehow this electrical current created like this movement in the compass. And obviously we know that compasses are only affected by magnetic field, well, give or take only by magnetic fields, because that's why the whole Earth's like magnetic poles work, right? So basically what we realized was that an electric charge that is moving creates an electric field. Sorry, magnetic field, sorry. Um, and then by extension, what is a current carrying wire? So so electricity is moving electrons. What is electrons? Electrons are a charge. So moving charges, which are electrons, create a magnetic field. There you go. So two things is current carrying wire and moving charges. So those are the two things that create an electromagnet. But obviously they're interrelated. So basically because a current carrying wire is a moving charge. So I know they split it up, but it's technically the same thing, right? Um, check the chat. Oh, okay, cool. Sorry. Um, okay. So then, right after that, so then we realized, so okay, cool. This Ørsted guy saw that electric charges create a magnetic field. So then we all know the famous Ampere, right? He's the one who created amps, obviously. Um, Basically, he extended this. So he basically formulated that relationship between that electric current and that magnetic field. So what we know about Ampere's law, and we'll talk about this later. This is like the next slide of the next after that. But specifically, what I wanted to talk about in terms of Ampere was the right-hand rule. So we know him more for, I guess, like, the Ampere's law, but he does have this Ampere's right-hand rule, which we all know about. So it's basically, your fingers and then your thumb, right? So if your thumb is the current, the movement of the current, so let's just say this is the current carrying wire, and then you have electrons moving up that, so the current that's moving up that, sorry for the blur, and there you go. And then basically your thumb is the movement, so the direction of the current, and this will tell us, the fingers will tell us the direction of the magnetic field around the current. Okay, correct. So obviously this means like technically if you're looking at this way, so if the current is out of the page, right, your magnetic field will be going anti-clockwise, right? So that's basically how you figure out the direction of a magnetic field around a like a current carrying wire or even a charge as well. So that's the important section that we need to know about like Ampere's right-hand rule in this case, right? Just really quickly as well, like this image that I have, it's not a completely random image. It's actually like again some sort of like real life kind of application. It's really important, like interesting to know these, and I think it's again aided in my understanding of the physics as well. So you see the image, right? You see, obviously you guys must have seen these like electric power lines before, right? These ones like carry tons of voltage, right? And well, technically lower current because if it's a higher voltage, right? So these essentially have bunches of like voltages going through, And what happens when you have a large voltage or large current going through? Basically, what happens is it creates that magnetic field. So you can imagine when you go close to these, you should be able to feel the magnetic field. That's how like strong this like current that's going through them like wires are, right? So they actually have caution like signs on it. They say like, oh, don't go within 150 meters of it or 100 meters of it, not because of the electricity that's passing through it, but because of the magnetic field. So it's so interesting to see this, even though these are insulated and like, obviously we have like wires that are here like that we see every day, but they don't produce, I mean, they do produce the magnetic field, but they're so negligible, right? But obviously at this rate, at these tons and tons of voltages that are going through these wires, it's an immense amount of magnetic field that's going through it. Um, so that it's actually above the safe level of like magnetism, like Tesla, the amount of Teslas that you want to like get in like when you go near these electric power lines, which is really interesting. So um, technically, there's more a higher magnetic field in MRIs, but there's obviously one-time things and very important. But yeah, so that's a very important phenomenon. What's that? Okay, no, I'm assuming. Okay, cool. So yeah, so that's a very important phenomenon. So I'll be talking a few about these phenomenons like throughout the thing as well, because this is very important to know what we figured out as a as a human race, like what we figured out, and what we just randomly saw, right? Like what we just saw happen and what we figured out from there, right? So keep in mind this magnetic field, right? So basically what I've talked about so far, the main like message is that moving electric charges, and um, and current carrying wires basically produce a magnetic field. Okay, so I've just seen a question. What's Fleming's left-hand rule with your right hand? Oh yes, okay. So I will talk about this actually. It's very confusing. So yeah, I'll bring this up. So left hand is generally for motors, which is what we'll be talking about, but I'll bring up what the right hand does as well. That's a very good question. It's an important distinction to make later on. So I'll come back to that. All right. So what do we have? So okay, yeah. So right here, so we have Ampere's law now. So I technically should have put this image in the previous one, but you can see how Ampere's right-hand rule works here. And then Ampere's law is there. We've seen this in bunches of time, right? So you've got the U naught, that's the constant. So that's what we call the permeability of free space, right? So that's basically how much it like permeates through the free space, right? Which is pretty straightforward. It's a constant, which means like, through the air, what atmosphere, what we have right now is that permeability. So that's a constant, right? I is obviously current, R is distance, pretty straightforward, right? So this is basically the like how you figure out the magnetic field strength, which is obviously B, that's the magnetic field strength. And how you work that out based on the current and the radius of that as well. So that's pretty straightforward. Okay, yes. So solenoid. So this is a very important concept now. Um, so what is a solenoid, basically? So it's basically a coil of wire. It's very, very like it's a basic thing, right? So it's this coil of wire, and basically when an electric flows through it, like electricity flows through it or current flows through it, there's a magnetic field. Okay. So how do we see that happening, right? We see that happening is, remember when I said when a current goes through a wire, so just a normal wire, let's just take this wire, for example, you have a magnetic field going around it, right? But now it's coiled now. It's not no longer just a linear line. It's not like a line anymore, right? So yes, it is from the Oxford textbook. Yes. So I got a lot of the images from there. That's what I used as well. So but yeah. So this is the coil of wire. So now when we have a coil of wire and then there's a current going through that, the magnetic field is obviously not on every individual like level, is not forming like that because then it's not uniform. That's not how magnetic fields form, right? So what we see is that the solenoid actually forms a magnet similar to a permanent bar magnet, right? Where we have the north pole and we have a south pole. So the important thing is to understand is similar to a bar magnet, a uniform magnet, a solenoid still has a uniform magnetic field. And it's parallel to the axis of the solenoid, right? So that is the slight difference, or because of the bar magnet, because have it going through, like the magnetic fields going through the solenoid, kind of, right? So it's slightly a bit more complex than like a bar magnet, but the kind of like the basis is the same, right? So keep in mind again as well, so this one's a bit more straightforward. You can see through the like the formula there. So like the magnetic field strength is given by B equals, again, the permeability to free air space, N times I. So that basically can determine how much magnetic field strength you get. So if you have a higher current, obviously you'll form a higher magnetic field strength. If you have more coils, then you will get a higher magnetic field strength. This is actually very important as well, that formula, because we'll talk about it later in transformers and how this relates. So keep that in mind as well. Now, solenoids, basically, because we see electricity converting to a bar magnet almost, that is the reason why they're called an electromagnet. That's basically what we call an electromagnet, an electricity-induced magnet, basically, right? So basically the direction, right? We've talked about, north and south pole, right? We can figure this out now by the same Ampere's right-hand rule, right? So now instead we see that there's the direction of current is in a circular pattern versus the direction of current that we saw in the previous one. Remember, the previous image was the direction of the magnetic field was circular, but now the direction of the magnetic field is now circular, right? So similar to how the image is doing. So basically, if you have now, like, let's just take this water bottle, right? This is a solenoid, right? There's a current going through this right now. This basically, if the currents will all be going down in one direction, because obviously when it goes in a circle like this, in one area, it'll be all going down. So this is the one thing that you need to keep in mind. A lot of people get confused here, and I'm sure you guys are not, but I'll mention it anyway. Is like they're asking, like, where do we take the direction of the current, right? The direction of the current is either taken from one direction. So if it's this direction, take it from this direction. Just be consistent with it, right? So if it's going down here, your finger should be going down like that. And then because of that, where's your thumb pointing now? It's pointing that way. So that's where your North Pole is. Yeah, so your North Pole, it basically directs your North Pole, right? So it's a bit confusing because Ampere's right-hand rule is for the previous example where it tells you the direction of the magnetic field, but in this case it tells you like it's a bit switched over. So yeah. So um yeah, so as I mentioned, it's pretty similar to a bar magnet. So don't get too like, confused about that. There is a defined North Pole, there is a defined South Pole. But the I guess the question you guys might have is like, why do we need an electromagnet? What's the point of it? So it's actually incredibly important because the thing with bar magnets are, first of all, they're not controlled, so we can't control them, right? So obviously humans love stuff that we can control. So electromagnets you can control with like the number of coils, with the number of current. The biggest thing is you can turn them on and off, right? Electromagnets you can just turn them off. There's no magnetic field. So there's like primarily actuators, so you can see them in motors where we talk about it later on. That's the primary reason that we use electromagnets. But you have all these like tiny areas that we use electromagnets, kind of like loudspeakers, generators, motors, which we'll talk about later. That's like the primary places that we use it. So it's in like tons of places that you guys like we see every day, basically. Actually, for my IA2 student experiment, we like built a pneumatic electric projectile launcher. So it's basically we can manage the pressure. We basically put in air so that we like build the pressure inside the chamber, and then we use an electric kind of button to essentially like shoot the projectile. So the way we did that, we actually got a solenoid, and then that's how we kind of induced like the current within inside that, basically. So we got that solenoid from I think it was a um what do you call it, like a regulator, where you have like the water tap regulator. So that's kind of like that. The point being that it's very useful. So yeah. Let me check the chat really quickly now. Why is it important that the power lines you showed before have high voltage if it isn't featured in the magnetic field equation? Wait, sorry. Wait, sorry, what do you mean when if it isn't featured in the magnetic field equation? Oh, do you mean like, oh, okay, yeah, exactly. Just like the person said, yeah, voltage is related to current, exactly. Yeah. Exactly correct. So obviously voltages and current is just inversely related, like it's just inversely proportional. So, you have high voltage, low current, etc., like similar to that. So, because the thing is like when we're working with like massive electric field lines as like that, even though the higher the voltage, the lower the current, you can obviously reduce resistance. That's one way, obviously. But then the other way is like you still have like what, like 150,000 like volts, which is still relatively a high current, even though relatively to the voltage, the current is lower. It's still like a gigantic amount of current, which means that it'll produce still a massive magnetic field, right? So, but yeah, that's a good question though. Like, yeah, but it's because you have like they come together basically, just like electricity and magnetism. You can't have one without the other. All right. Okay, so now we're getting into kind of like the really good part of, I would say, of electromagnetism, the interesting part, if you will. Um, okay, now we see like another phenomenon kind of thing, right? So we see a charged particle. What happens if a charged particle now, or a current carrying wire, remember, because they're both very similar, what if that moves through a magnetic field? Well, rather than moving, what if it's just inside the magnetic field? You will get a force. And that's what we call the Lorentz force, right? So the Lorentz force is a combination. So a lot of people have the question, what's the difference between Lorentz force and the magnetic force? Magnetic force is a part of the Lorentz force. So the Lorentz force is magnetic force plus the electric force, right? Because magnetic force is purely by the magnetic field, right? So like, there's a force that's like, oh, hold on. Let me see. Question. Okay, yeah, okay. Cool. So, yeah, if you see that there is a force, Lorentz force, sorry, that it's means that it's like a combination of the two. So the magnetic force plus the electric force. But you don't need to get into the too much of details. But you can see that's the first one is basically where you see velocity involved. So if it's a charged particle going through a magnetic field, you have obviously the charge of the actual particle, your velocity of it, the magnetic field, that strength of the magnetic field you're going through, and then sine theta. For those who are doing like specialist maths, think of these are all vectors at the end of the day. Um, it's basically the cross product of both like the because at the end the force is like a vector, right? So you see magnetic field strength, which is a vector. Magnetic fields are vectors, right? And then you see obviously like velocity is obviously a vector. So technically you have the cross product of the two, which is why you have sine theta. So um yeah. So for those people who do specialist maths, that's a really interesting thing because like you will be covering like forces kind of in specialist maths as well. So yeah. So we see that's on a moving charge. The next formula is probably the most famous formula, the one that you'll be covering like so much. It's F equals BIL sine theta, right? The B is magnetic field, I is current, L is the length. And basically this one, even though it is more famous, it is derived from the one above. It's basically saying that the length, right? Length is basically the current that's going through it, basically. So they've kind of like brought in velocity and charge into the kind of like the length and the current there, because charge is more dependent on if you have a negative positive charge, but then they assume current is electrons, right, passing through. So um so yeah, oh whoops, switch sides. So yeah. So that's another like the force. But keep in mind, the other thing is important to know as well with both of these is like for the Lorentz force as well, the force is perpendicular to both the velocity that we see on the particle and the magnetic field, right? Sorry, of the particle and the magnetic field, right? So this makes it basically curve in a magnetic field. And you guys will see this in like pictures and questions. It'll basically curve. Don't worry about that. All you need to know is the direction of like general direction of movement. But because the force is perpendicular, which we'll come back to with these like things, right? It'll create a curved path, right? And basically, how we find the direction of the force, how do we find the direction? We use that Fleming's left hand rule, right? Which was, someone in the chat mentioned earlier, right? So this works for current carrying wire in a magnetic field, right? Generally, we always see that there. So basically, you hold your left hand like this. If you guys have never done it before, thumb up, uh, index finger straight ahead, or like just like normal, right? So if you have it like this, thumb up, keep your index finger, and then the middle finger just like goes in, and then just fold the other ones if you guys haven't done that before. But basically, very easy to remember. So just imagine top to bottom, right? So you have FBI, right? FBI. So force, magnetic field, I. The FBIL. So sorry, there's no L, but like I'm saying, like in terms of the order of the actual formula is the order of how much like the fingers there, right? So obviously you've got the force up here, the current here, and the uh the magnetic field here and the current here. So that's how you basically use Fleming's left-hand rule. It's pretty straightforward after that. So um, yeah, the FBI. Okay, cool. Yeah, exactly. So and then we obviously talked about the FQVB. So you use a similar thing, but I'll talk about more like specifics about FQVB with this because it differs on whether it's a negative positive charge. Um, so yeah. Okay, cool. Keep both of these things in mind because we'll be talking about that in a lot of depth when we talk about motors later on and like generators. So keep that in mind. And obviously like the positive negative charges that I'll be mentioning later on as well. Okay, here we are. Okay, now this is one of the application things that are quite important. So a lot of the other application stuff I just like say because it's very interesting and it is actually quite like, it's important for your understanding. But this is genuinely something that could be tested on. So this is important. Okay. So, okay, loudspeaker stuff, probably not, but I'm going to mention them anyway. So, okay, how does loudspeakers work? Okay, this is super interesting, but you can look at the image there, right? So you see that they've labeled the cone and you've got the voice coil and you've got the magnet, okay? So the first question that you guys will be like, why is there like south pole, right? Why is there a south there, right? So the reason is because remember what do solenoids do in the middle, right? Technically, let's just say it's a coil for now. So when the current is passed through the coil that's inside the magnetic field, what happens? Basically, you have an alteration. So there's a pole, it creates a pole first, right? But there's an alteration of north and south pole. Now the question is, why do you have an alteration? Like, why is it altering from north to south? Actually, I'm gonna pose that question actually. This is very interesting if you guys like just chuck it in the chat. If you guys like why do you think the pole so that one says north on the picture? Yes, good, exactly. AC current. Good. Really good. Um so AC current is the reason why we have the north and south pole differing in like the coil that we have there, right? So AC current, which we'll again talk about in electric generators and motors, but basically it's where it goes back and forth, basically, right? The current, if you can imagine like electrons going back and forth in a wire, so it's kind of like counterproductive, but like that's how it's formed. Like that's just how it's made in like in hydropower wind turbine. That's just how like uh electricity is made. It's made through AC current mostly, right? So when you have an AC current going through that, you have an alteration of direction of the current in the coils. So if this is the coil again, the electricity will be going down, then it will be going up, down, up, down, up, down, up. So it'll be just basically like really quickly going up and down, up and down. And when it's changing the direction within the coils, what happens? Remember Ampere's right hand rule. So it's going down, North Pole, and if it's going up, that's North Pole. So it's basically switching between North and South Pole. So when you have an altering current within a solenoid or a coil of wire, the electromagnetic changes poles. So you see a North and South pole changing, basically. So when you see a altering of north and south pole in that coil, what will happen to the south poles? It will start attracting to the south poles when it's a north, and it will repel if it's a south. So then you'll have like this basically this altering like basically it hitting the cone of this like um attraction and repulsion. It'll just be repelling, attracting at a very fast rate, and that is what you cause the vibrations of the cone, and that's what creates a sound wave. So it's very smart. I don't know, like if you guys have realized this, but it's a very interesting, very smart way to do it. But they basically use an electromagnet and the AC current, which is what we produce anyway. So just keep in mind, just really quickly going over AC versus DC current, because this is also incredibly important for transformers. Batteries, solar power. As far as I know, those are the only two things that produce DC, direct current. Every other form of like electricity that we produce is AC current. Wind turbines, hydropower, fossil fuels, those are all AC current. The reason is because of a turbine that's being produced, and I'll talk about that later, but that's what's producing the AC current, right? So your like laptops, obviously, they're all DC. They take DC because they have a battery, right? But you charge it from a power point which uses AC current, right? So that's why generally you guys have that like that's why you guys have like inverters to change it from AC to DC, right? You guys have all devices generally like your house appliances should have a conversion of like AC to DC current, right? So yeah, so that's very important to know. So in this case, they use an existing thing. We have AC that's always used, that just basically converts the electromagnet from north to south, which essentially uses the attraction and repulsion to form sound, basically. So that's loudspeakers. Now, I'll talk about electric motors and generators, and this is probably where if you guys haven't, which understandably, if you guys haven't been tuning in, you probably should be tuning in now. The motors are probably the more interesting, not interesting, well, interesting, but also more important. Okay, take a look at the diagram there. So you see a magnet, you have a South Pole magnet there, and you see a North Pole there. You have a coil of wire going through that, so a square coil, right? And then you have this thing called a slip ring. So it's basically where when it turns, it needs to turn without like the slip ring turning because you need to have connected cables to it. So you see that there's a connect like the cables positive and negative there. Obviously, you don't want that turning as well. Otherwise, you're going to have like a, like a tangled cord. So that's why you have the slip ring to make sure it turns without, but while also transferring like current, electricity through. Okay. Okay. So what do motors do? What do motors do? They produce a force from electricity, right? That's what Teslas do. That's what EVs do, right? They have batteries which send electricity to produce a force, which in that case, sorry, is like movement of wheels, the movement of the axle which moves wheels, which goes forward, right? So this is where the Lorentz force comes in. You essentially put in, right, electricity, right, through the, obviously you got the negative positive. You put it through, like, say, just this is like obviously an example, but you put it through a battery where you see the current. Do you guys see the current that's going through? It's I guess you could say it's going clockwise, right, in the um like clockwise in the square coil. And then you guys see that force that's going up and down, and then that's because of that magnetic field. All right. Now, remember Fleming's left-hand rule? Let's try that, okay? So current, so FBI, okay? So where does the magnetic fields go from? It goes from north to south, so FB, so it's going from north to south. Then you have current, which is going forward, right, on the left-hand side. So remember, just take one section of the coil first, okay? One section. So I'm looking at the left-hand side of the coil, right? The current is going up the coil. So that means the force is going up, which is correct, right? So you see the green, sorry, I'm colorblind, sorry, but like I think that's a green arrow. Green arrow which has force, that is the force that's going up, right? And then same thing for the other side. So on the right-hand side where you have the, okay, thank you, green. Okay, so if you have the other side going down, the force going down, let's try that as well. So FBI, B is magnetic field, so north to south. Then you have current, which is going down, and then therefore the force is going down, all right? So that's I guess we've just verified the Fleming's left-hand rule for that. So that is how like force is created from electricity, right? because essentially now I'll just quickly explain it again. But if you have basically the two phenomena that I'm going to explain now is magnetic field. Let's just imagine there's a magnetic field here. If you put in a force, if you apply a force, you will induce a current in the wire or whatever the conductor you're doing that with. If you put in a current into the conductor, which is inside the magnetic field, it will produce a force. So the conductor will go out, or like, whichever way the force is acting on. All right? Does that make sense? And there's two sides of it. So I'll repeat it. If you apply the force in a magnetic field, it will induce a current. So that's what we'll be talking about later, electromagnetic induction. But for now, what we're talking about is where we put in a current or electricity into a conductor, which will produce a force. So in this case, if I put this in with the current, it will like fly out, right? Because that's the force. Okay. Let me check the chat now really quickly. Okay, cool. Yes, it is very interesting. Cool. Okay. So that is motors, and then generator is just the other way around. So what I just mentioned basically. So when you apply a force and it produces current. So it's basically the exact same thing as what you see in that image there. But imagine um, where, for example, in wind turbines, right, you're turning a turbine, right? And that turns this square coil. You turn that square coil within the magnetic field. And what happens when you apply a force in a magnetic field in a conductor? It produces an electricity or a current. So that's what you're going to see in a generator. And in generators is when you use Fleming's right-hand rule. So for the person who asked that question and for anybody else here, use Fleming's right-hand rule for that. So remember, left hand is for motors, or in other words, something that's producing a force. And then the Fleming's right-hand rule is for generators, which produces a current. So the way I remember it is, I'm not sure if you guys are like, I'm sure you guys are old enough, but like, I'm not sure if you guys remember like the things that you like turn around to create electricity, like the torch. So you have a torch and there's like a handle and you like do this and you power it, right? So that's how I remember because you're generating electricity in that case. So that's how I remember it. And you do it with your right hand, the dominant hand. So I just remember dominant is generator, left is like motor. Generally, you'll most likely get motor, but just keep in mind just in case if you get generator. Um, so wait, why? Um, okay, cool. Right, let's go to the next slide. Yes, okay. So electromagnetic induction. So this is probably where it gets like a little bit more difficult, but also it kind of gets easier because if you know like what the basics are, right? So let's start with magnetic flux, right? So what is magnetic flux? It's basically the amount of magnetic field that's going through a certain area, right? So if we just say like, I don't know, 10 square centimeters, how much magnetic field is going through that is what your magnetic flux is. And um, that's obviously like in Weber. So that's by the guy who like founded obviously. So the scientist behind that. So you see that obviously that there's a magnetic field times that by the area times that by cos theta. So whether or not it's perpendicular to the field. So I've copied in like 3 examples there. We have 0 degrees, 50 degrees, and 90 degrees, and you can see like whether it's like perpendicular or not. So um, and that's obviously changes in the cos theta part of it. So yeah. Okay, cool. So that should be pretty straightforward. And just to keep in mind, I know I said square centimeters, but obviously area when you're subbing it in, it should be in square meters. So because that's the SI unit for it. So well, for distance anyway. So yeah. Um, okay, so then that's probably not as important. The magnetic flux density and then thus the electromagnetic induction is probably more important. So magnetic flux density. What is magnetic flux density? It's basically your magnetic flux. So how much is magnetic field is going through per unit area. It's not a given area, it's per unit area, if that makes sense. So That's important to understand. And that is equal to the magnetic field strength. So remember we talked about density at the start? It's the same thing, basically. So magnetic flux density, the amount of magnetic field lines or whatever going through a given area or, per unit area is basically how you can quantify magnetic field strength, right? Okay. So then we've got electromagnetic induction. So this is probably the most important part of it. So obviously this is so we have a magnetic field. It produces an EMF, so electromotive force. So that's basically, just think of it as a current for now, right? And obviously Faraday is the one who found this. That's why we see Faraday's law next. But Faraday is the one who found this out, and that's related to what I just mentioned before in the generator, right? So it's basically where it showed if you changed the magnetic field within a loop of wire, right? So similar to what I talked about before. So say you change that magnetic field, right? And then there's a loop of wire that's going through it. That EMF is induced in that wire, and that obviously causes that like the current to flow through that, basically. So it depends on, it's slightly different to what we covered before. So where that one was like related to a force, but this one's more if you change the magnetic field. So it's either one like moving, one or the other is moving, if that makes sense. So in this case, you see a magnetic field movement which induces a current, basically. And as I mentioned, this is basically how generators work. So obviously when that coil of wire, right, it moves through that magnetic field, and that change in that magnetic flux through that coil, that is what that induces the EMF in the wire, right? So if that coil, like it's part of like the closed circuit, if it's part of a closed circuit, then that's when the electric current is generated, right? Okay. Um, And yeah, so this is kind of like what's related to transformers as well. So which is what we'll discuss next, or not next, but the one after that. Um, yes. Okay. Awesome. Let me just check the chat real quickly. All right. Cool. Oh, okay. So yeah, here. Um, is the EMF electromotive force electromagnetic force? No, so they're different. So electromotive force is what we're talking about. So EMF is like the current that's induced, right? Current. Technically, they like also you might be able to see voltage, like what do you call it, potential difference sometimes as well. So but no, yeah, they're not the same thing. Good question though. All right, we'll talk about Faraday's law. So this is probably a really probably the most important part of this lecture now, as part like which relates to transformers as well. So this Faraday's law basically tells, how the like the EMF is induced in a circuit, so that how that like the current, the electricity is induced in that circuit when that magnetic flux is in the circuit changes, right? So that's what we see in that, like the mathematical formula right there, right? The formula that we just copied off from the physics formula sheet. You see that there's an EMF, and then basically you have the magnetic flux on the top, and then it's basically over time, right? So you can see that there's the first formula that's basically like the second formula, right? They're the same thing. It's just the difference is the BA is just expanded from the magnetic flux, basically. But what it's saying is that the EMF, the induced EMF, is proportional to that rate of change of the magnetic flux. Okay. And the negative sign is very important. That just means that the induced EMF opposes the change in that magnetic flux. Okay. This is very important because that's the whole point of Lenz's law. Okay. But we'll come back to that. But that's essentially how like the law of conservation is like, maintained, right? So okay, let's go for an example right now, right? So when you bring a magnet, right, near a coil, right? You bring a magnet near a coil, what do you have? There's the magnetic flux through the coil that increases. Okay. So according to Faraday's law, what you'll see is the change induces the EMF. You'll have a change that induces the EMF in the coil, which drives the current. So that's like the distinction between EMF and current there, right? EMF kind of drives that. So that's why it's like the voltage in a way, the potential difference, right? Voltage is what drives the current, but occasionally they use that interchangeably, which is not that good, but we'll keep at it there. But um, so again, I'll just mention it again. So when you bring a magnet near a coil, you have the flux through that, which increases. Okay. So that change in magnetic flux is what induces the EMF, which drives that current. So that's what you see here as well. All right. You see that when you increase that magnetic flux, which is the top part of the numerator of that formula, it induces that EMF there. All right. Okay. So yeah, let me know if you guys have any questions as well. Yeah. Okay. Awesome. All right. I'll just Okay. Cool. Let's head to the next one. Hopefully we can finish this soon enough. All right. So Lenz's law. This is probably the most confusing law, actually. Um, I will have to admit it's a bit annoying that I can't draw at the moment. I want to draw later on. Hopefully it's going to work out for the transformers part. But showing you is probably easiest. But because I can't do that, I can refer to you to. Okay, good. There's some people who like Lenz as well. Okay. There's a really good Khan Academy video on it, actually, if you guys want to see it. But that's like what they tell it you in a very good way. But I'll mention it as well. So basically, what you see is that if Faraday's law is, let's say, it's taken just as Faraday's law, it technically violates the law of conservation of energy, right? So I'm not going to say Faraday's law violates it, but the way you interpret it could be, right? But with Lenz's law, it's like the direct consequence of it, right? So basically, Lenz's law is a direct consequence of Faraday's law of induction, basically, what we just talked about before, right? So it basically states, right, so the direction of that induced current, so we have a magnetic field. So for example, when you put a magnet near a coil, right, you have an induced current. That current will have what? Will have a magnetic field as well, right? So the thing is that they saying that that induced current will oppose the change in the magnetic flux that caused it. Okay, so remember we have like the magnetic flux, right? That induces that current. What they're saying is the direction of that current is opposite, so it will oppose that change in magnetic flux. So okay, now let's say if it didn't oppose it, right? So let's say it induces that magnet induces the EMF within the wire, right? Now you have a current going through the wire, and the current going through the wire creates what? It creates a magnetic field, right? And if that magnetic field is in the same direction as the magnetic field that essentially induced it, it will add together. The magnetic field will add together, and if those add together, it'll induce a larger current, and that larger current will produce a larger magnetic field that will add up to create a larger magnetic field, which will induce a larger current, and it'll just go on forever, which means you'll be creating energy out of nowhere, basically. And that is a violation of the law of conservation of energy, right? So what we see instead, right, and this is Lenz's law, so he's basically saying a law that's like there already, right? He's saying that basically that induced current will be in the opposite direction, so that the magnetic field that is produced, like the magnetic field that electrical current produces, opposes that magnetic field that created that current. So then that magnetic field will cancel out and it'll slowly degrade over time, which makes sense because you have energy losses generally. So that's what is basically Lenz's law. So that opposing force that we see ensures that, like, that energy is not created or destroyed, basically, in that process, in that electromagnetic induction process, basically, right? So people say it's like a safeguard for energy conservation, but obviously it's not. Like it's there, right? Like it's not something we do. It's not something we conserve, right? It's just how it's induced, because otherwise it wouldn't make any sense. So, um, yeah. So that's basically Lenz's law. Let me check the chat really quickly. Where does the wait, hold on. I'll answer the question above. Oh wait. Actually, let me check the Slido if anybody's asked any questions. Okay, what are some tips to get 100 in physics? I'll mention that at the end. Will we have access to PowerPoint? Okay, cool. We answered that. Mark has answered. Is Unit 4 physics hard? I'll come back to that. What is Laplace's law? Interesting. Okay, haven't heard of that. Let's delete that one. Okay, cool. And yeah, where does the lost energy go? Yeah, as it's not lost. It's like it's where the magnetic field. Sorry if I mentioned lost, but like it's similar to like you would lose it because you're canceling out the magnetic field, which then produces a less magnetic field, which induces a less like electric current in EMF, if that makes sense. So it's not lost, but like it's not lost in the sense like resistance of a wire lost, that kind of loss. It's a loss in terms of like you have an overall loss in like magnetic field and thus the induced current over time, if that makes sense. Um, so yeah. So what we oh, what was the question? Yeah. Cool. Okay. So let's quickly do an example as well. So of like Lenz's law. So if we have like remember that magnet going towards core, so that's like similar to the image that actually we see there, right? Um, So we have a magnet going towards a coil, and then as the magnet approaches that coil, there's a remember the magnetic flux, right? That goes through the coil that increases, right? So according to Faraday's law, you'd see that this induces an EMF, right? And thus the drives that current, as we talked about. But that Lenz's law essentially ensures that that induced current is in a certain direction that opposes that approach of that magnet essentially. So yeah, this doesn't necessarily mention that, but the image, but that's basically the current direction will basically oppose that magnetic field that is produced by the magnet that induced the current in the first place. That's why it's very confusing when you read like the QCAA definition as well. It's super confusing. Um, yeah. Um, So yeah, and as you can see here in this image as well, so you see it going in, right, which induces a current. But as you can see, if you pull the current away, that the induced current basically will try and attract that magnet, and that's part of Lenz's law because it opposes the decrease in magnetic flux now, right? Because when you pull the magnet away from the coil, now the magnetic flux decreases, not increases anymore. So when it decreases the magnetic flux, it now attracts it, right? Before it repelled it, similar in that first image, but now it is attracting it, right? So that is a way that's essentially the other side of Lenz's law, where it essentially opposes in that kind of like way, where it like attracts it now, basically. So so that's like, it works both ways. It's not like a one-sided kind of repulsion, like reduction of kind of magnetic field in that case. Um, yeah. We see this a lot of things like again like in generators and like what I've talked about is before. So yeah, that's basically Lenz's law. All right, transformers. Okay, cool. So this is the part where I need to figure this out because um obviously I don't have well, I specifically didn't put anything on there because I wanted to bring out a whiteboard. If anybody knows how to put a whiteboard on Discord, please let me know. On PowerPoint. Oh yeah. Okay, yeah, you're right. There on PowerPoint there is, but the issue is it's gonna be through my mouse. Hopefully you guys won't mind me using the mouse. Let's just okay. Just for the sake of like time, I'm just gonna use my mouse. That's okay. It's gonna be really bad drawing there. Okay. Okay, cool. So this is my favorite part. And this is actually the one that came on my exam as well. So I was so happy to receive this. I thought it was like such a pointless thing when I did not cover transformers until the night before the external exam. I was going through every syllabus point, and I was like, wait, I never saw that syllabus point before about transformers, and I was like, I should probably cover it just in case, and I covered it. Next day, physics exam said, I think it was like explain how transformers work in terms of like Faraday's law or something, which is insane. So I'm like, thank God. Um, I graduated 2021. So yeah, it's probably you can just like search up the exam. It's probably on there as well. So um, oh yeah, sorry. I'll answer this question as well. But I think Dish, you did it. But let me see. Anyone explain the motor thing? So they give it a current, and then it makes a force on alternate sides, making it move. Then how do they get the energy from that? No, no. Okay. Yeah. Okay. So you're correct that it makes a force. So obviously, because of the Fleming's left-hand rule, you have a different force on one side of the coil versus the other side because of the opposite directions of current, but you don't get energy from it. So this is where you put in electrical energy to create a mechanical energy or create a force. Okay. Generators is where you get the energy or the electricity from it, right? So it's, for example, in Teslas, like you would power that to essentially like create like make the car move, which is the force, right? So yeah, so the alternate sides, okay, essentially alternate sides basically makes the coil move in a circle. Because if you imagine, right, this, you have the force of this side going up, the force on this side going down, what will happen? It'll just go in a circle, right? So you'll see that moving in a circle, and that's actually basically what happens, like, normally as well. So that's your kind of force that's created. So so um yeah, exactly. So yeah, it's basically what dish does. So it allows you to convert the energy into a current. So yeah, yeah, exactly. For generators, it allows you to convert the energy into the current into the rotational force. Yeah, cool. Yeah, sorry if I confused you guys with the generators. But just imagine generators is the opposite of motors. Just know motors specifically. If you guys like can't figure it out, just do motors. Just figure out motors. Even if you're going to sacrifice the generators one don't mean much. So, um, yeah. Um, yes, exactly. Ashan, yes. That's exactly correct. Cool. Okay. Um, so transformers. Okay, yeah. Okay, cool. So let me try and draw on this. Okay. So what are transformers? What do they do? Very important. Okay. We get current. We get electricity from what? Fossil fuels, like what I said before, like, wind turbines, hydropower, right? For reference, you probably get around, like, this is, I think, just for the sake of explaining it, it's probably going to be like 100 kilowatt. So it's 100,000 volts, right? Of of power, right? Of like electricity, right? But when you bring that power, that electricity to your PowerPoint, what's the problem? If you touch it, you'll be cooked immediately. Like, right? Like you'll be dead in like less than a second, right? So that incredibly high voltage, yeah, exactly, it's unsafe. So it is incredibly unsafe if you just bring straight away 100 kilovolts of energy straight down to your power outlet, right? So what do you need to do? You need to reduce the voltage, right? So you reduce the voltage so it's safer for us in the houses. So for reference, guys, your normal PowerPoint, your standard like Australian PowerPoint is about 240 volts, right? So that is, I would say, even that is on the borderline of safe. But it's obviously way safer than 100,000 volts, right? Now the question you guys might have is, why don't you just have a gigantic transformer right at the, substation that produces the like electricity, and then just go from there? That is because if as soon as you decrease voltage, you increase. Let's see. Sorry, no, I just saw some chat. So yeah, exactly correct. Because the high voltage has greater inertia. Exactly. So when you decrease the voltage, you increase the current as well, which means you can't travel far. You can't send the electricity so far, right? From the grid to your house is probably like, yeah, dish is cooking. Exactly. Um, so you can't travel far with that, right? So when you have a high current, low voltage, you can't travel far. So what we do is basically we make it essentially travel far with the high voltage all the way to a substation, maybe a local substation, that will maybe reduce it to say maybe 20 kilovolts, right? And then that 20 kilovolts will go to your basically a transformer maybe outside your house, closer to your house, like those electrical boxes that will transfer it to 240 volts. Or actually no, I think some of it goes to 400 volts or something because if you have air conditioning, your air conditioning will use like 400 volts, right? Whereas the rest of your house will then be like it will be transformed to 240. So point being, transformers are really important for like essentially making sure electricity can travel far, but as well as it's safe for people who use that like electricity, right? So basically what we need is to reduce or increase the voltage. So it's all about voltage. So when you have a step up step up transformer, it steps up or increases the voltage. If you have a step down transformer, it decreases the voltage, right? So how do transformers look like? You have basically, oh, whoa. You basically have a coil kind of. Let's just simply draw it as like, so these are like basically, let's just say they're iron cores, right? They're very like thick iron cores, right? Um, that's not supposed to happen this line. There we go. So basically what we have is this will have a coil around it, around the iron core there. And obviously this will be connected to the power. So the electricity is going this way from like, the power lines way after you've generated it, right? And then this will basically go around and then will be on this side of the coils, right? And that'll generate electricity. That'll send the electricity that way, right? So how this works is basically electricity will be coming through a coil, right? What happens when you have an electricity going through a coil? Produces a magnetic field, right? Because that's what we've been talking about this whole time with solenoids, right? You have a magnetic field that's being produced, right? I should say this way for now. I'm not sure what direction. I won't bother with that right now, but let's just say it's going like that. Now, the question is, what are we going to do with this magnetic field? What's the point of it? The point of it is, remember we talked about earlier, what's the electricity that's coming through here? AC current. What does AC current mean? AC current means that it's alternating current. So if you have an alteration of the current going through here, you have a movement of the magnetic field. So you have an oscillation of the magnetic field, if you will. And if you have a changing magnetic field, is what? It's that magnetic flux that we were talking about, basically, right? So that induces the current, basically. So you have the other side of coils, right? Oh, whoops, what just happened? Apologies. All right, there we go, back. Okay. So, yeah. So when you have a changing magnetic field, what will happen to the other field? Like the other coils on the other side, sorry. Oh, sorry. Yeah, okay. There you go. Okay, awesome. Cool. Okay. So yeah, thank you for pointing that out. So when you have this changing now magnetic field, so remember because of the AC current, it's alternating. So it's going this way, that way, this way, that way, which will change the magnetic field. So it'll make it like bigger, smaller, it'll change the direction as well, right? So when you have that AC current going through, you have a movement of the magnetic field. That magnetic field will, remember in electromagnetic induction, what's Faraday's law? That'll induce a current, right? Faraday's law is that an EMF is induced, right, in like a conductor or whatever it is, when that magnetic flux through the circuit changes, right? So you have this magnetic flux changing now, right? Because of the AC current, the magnetic field is changing. That's magnetic flux is changing. So when you have a changing magnetic flux, it affects the coils in here and induces that current into here. Do you guys see how that works, right? So that because of Faraday's law, that change in magnetic flux can induce a current all the way here. Like these are not even connected, but this magnetic flux can that change in magnetic flux can create a current on the other side. And obviously how you step it down or step it up is just dependent on the number of coils. So if you have like 1,000 coils here, if you have 1,000 coils here, and you have 100 coils here, that's how you step down the voltage basically, right? So basically, this is how transformers work. Does the distance between them matter? Yeah, like basically, so generally they would have a standard, but the distance would matter because if you have it further apart, obviously then you have a less like magnetic flux going through, right? So I guess you could technically, yeah, you're right. You could technically create like a higher distance of like between the two ion cores technically, and that would like, can step down or step up. But obviously that's much less like efficient than like just changing the number of coils, right? So you could just have more coils and you could just have a standard distance. So um so the thing is with that is this basically induces a current here, right? Now like this is something that I thought of as well when like I was learning transformers. You can transfer current from one place to another, right? That is also actually how wireless chargers work in your phone. So you have a wireless charger, you connect it here. That's so that the magnetic fields basically can like work with the magnetic fields inside your phone, like the coils, and basically induce a current and charge your phone basically. So that's like it's like so interesting to see how it like how like this whole magnetic flux like changing and obviously transformers work, but that is for the most part how transformers work and how like Faraday's law, which is basically electromagnetic induction, works in to create like transformers, right? So let me check again the other thing if there's any relevant questions to this so far. Yeah, no, okay, that's all good. Cool. Okay. Oh wait, actually I just saw, does the thickness of the coils matter? Thickness of coils. Do you mean like the diameter of the coils here? Like that diameter? Or do you mean like the wire itself? Oh, and this one. Are they not connected? Yeah, yeah. So okay, this is where sorry, okay, yeah, this is a good point. This is where I wanted to mention that where I drew the line. This transformers are like they're not two iron cores separately. They're like a iron core that's like a square, if that makes sense. So the square iron core like this. If you guys have seen transformers like in any like if you've pulled apart something, they're literally like a square gigantic iron core. And then yeah, the wire just goes through that basically. So yeah, they are connected. Yeah. So I just made it like simplified it just to prove the kind of idea of it. But obviously in wireless charging, for example, there's nothing connected, right? So um okay, yeah, sorry. I'm going back to does thickness of coils matter? That is a good question. Um, I guess like thinking of the formula stuff, I can't see like any mathematical like I guess idea where you have like the diameter of the coils. But that's a good question though. I'm actually not sure. Uh, that's a good question. That's something you can probably search up. Um, so yeah, that's good. I'll think about that as well. I'll write that down because that's interesting to know. Okay. I think somewhat because of resistance, the wire itself. The wire goes back. The wire goes back after it coils from the top. Wait, what? After it coils from the top. Wait, sorry, what do you mean? Let me just bring up a picture of like a transformer and maybe that might be like, that'll just make it easier. Because like I know my drawing is like horrible. Um, Transformer. Oh, rip, not the movie. Okay, there we go. Yeah, see, yeah. So there's the iron core that's connected to it. Um, technically the iron core is connecting them here. So yes, yeah. They are separate circuits. Yeah. Whoops. So yeah, that is like basically how it works. So you can see the iron core is like a square here. I saw a question. Oh yeah, sorry. Yeah, you've already copied the exact same image in. Good job. Thank you. What was the question? So with the same voltage, difference radius wires might produce different currents. Oh, okay. Interesting. Yeah. Okay, that's good. And the current is what produces. Yeah, that's great. Yeah. So yeah, EMF is technically the driving force of current. So yeah, with the same voltage, different radius wires might produce currents. Different currents. That's actually interesting. Yeah. Thank you for that, Dish. That's really good. Um, yeah, the wire goes back in the diagram and larger reduce the resistance. Actually, yeah. So I guess now that I think of if you have a larger diameter, that means you would need more wire and therefore there would be more resistance. Yeah. Yeah, that's pretty good. Good job. As flowing through the iron core. Sorry, do you mean my image or the image that I've like copied into the chat? Flowing through the iron core. Oh, do you mean? Oh, yeah, true. There is something. Okay, let me check that. Oh, yes. So I think that's just like the magnetic flux changing essentially. So you can see that there is a like the magnetic flux, and you have obviously like when you're inducing current into that, that is still a conductor, right? So you'll have you know it's conducting basically. So um, you'll obviously have the current that's conducting from the actual like wires as well as through the transformer because of the magnetic flux changes too. So yeah. Yeah, exactly. The iron conducts the field better, yeah. Yeah, so obviously in the formulas that you have the physics in your physics formula sheet, they have primary and secondary. That's obviously the primary, meaning the one that you're entering with, and the one that's going outside is a secondary voltage. And then you have, yeah, primary windings, or what we say primary coils, the number of coils, and then the secondary number of coils on the other side of the transformer too. So, um, yeah, th those are really good questions as well. Good job. Cool. Um, Let me change back to pointer. Yeah, just declick that. Okay, there we go. Okay, cool. Final brief thing that I wanted to. Oh, okay, sorry, another question. Does the iron core of both solenoids need to be connected? Why do you need the bits in red? Oh, so this is basically what like Dish mentioned before. It basically helps with the conduction, right? Because technically, obviously when you put a phone on a wireless charger, that's basically no connection, right? So you can see how slow like wireless chargers have not come to the not even close to the amount of like transference of energy to like cables, right? And that's because there's a ton of lost energy, right? So that transformer core basically improves that, like it basically helps with the conduction, obviously. So um is this what all power lines have at the top? Yes, so some power lines. So the normal power lines that you see like will be like no transformers, but then there's an occasional power line that you'll have like a gigantic like thing near it. And that's basically, yeah, that's basically a transformer. So depending on um I'm assuming that's questions like how does the like electricity pass through. That's because what we took, like basically the Faraday's law, right? So when you have a change in magnetic flux, right? So you're changing thing, right? It will just induce a current in a conductor, right? So it doesn't have to be like what we mentioned, like the solenoid, right? So that just conduction will just induce that current. So you'll lose a lot less basically from it. Oh, so you have the connection. So So you have the connection between the two sides of it. Because if you didn't have the connection, it would be purely based on the change in magnetic flux, which you'll lose a lot of energy, similar to what I said about the wireless charger. So if you have your phone on a wireless charger, you can see how much energy is lost because it charges so slowly, right? So that helps with the conduction of the electricity across. Does that make sense? Yeah, let me know if it doesn't, but hopefully um yeah, is the point to slowly kill off voltage? Well, depends if you're doing a step up or step down, but generally, yeah, when you do step down voltages, yeah, that's basically the whole point. So with the question with Walter, so isn't it just the field on the left affecting the thing on the right? Correct, yes, that is true. However, the thing on the left is the one that's, the change in magnetic flux, right? That change in magnetic flux, if you purely went off, like, okay, let's have a world where you didn't have those two red things, right? The red like things connecting the iron core, right? You'd be purely basing it on the electromagnetic change on the first coil, inducing a current on the second coil. Okay? You will have lots of energy loss from that. All right? Again, similar to what I said about wireless charging, right? Now that you have that, that is an extra conductor that the electromagnetic change of the first coil can conduct electricity to. And also, like, you have passing on the electricity from the normal coils as well. So the primary amount of, like, the primary voltage coming in will be reduced depending on the number of, like, coils on the other side. But also you won't lose as much. Like, let's say you wanted to reduce it from 60 to 30. If you didn't have the red, you probably go from 60 to 10 or something, right? It's just an extension of the iron core. Are the coils touching the core or just surrounding it? Well, theoretically, like, not touching it, but I don't think they would be able to do it without touching it. Like, it doesn't, like, basically in, like, the normal, like, whatever you see in, like, the real, like, when you open up like a those battery packs or something with the transformer inside, you'll have it, like, tightly coiled around. It will be touching it in that case. But it should theoretically work without touching it because you have that magnetic flux. But I guess that's where you also have the energy loss from there too. Does that make sense? Yeah, okay. Good questions, by the way. Do you have any other questions? It's, yeah, good to clarify those things. But yeah, just basically to reduce energy losses, basically. Okay, final bit. Sorry to keep you guys waiting so long. But okay, so electromagnetic waves and radiation. It's kind of weird that they put this at the end, but basically, remember we talked about stationary charge. Stationary charge creates what? It creates a static electric field. Pretty straightforward, right? So this field, like, basically what you've seen, just extends outwards, so it just goes outwards in all directions of the charge, and, like, the strength obviously depends on the charge and obviously the direction, distance from it and stuff, right? So if the charge stays stationary, there's only an electric field, correct? Right? And it doesn't do anything, just an electric field with an electric charge, right? However, once you start moving it, what does it do? When the charge moves, so when you have an electric current, for example, or a charged particle, in motion, basically, that generates a magnetic field. Remember we talked about that, right? It generates a magnetic field. And this is because, like, that moving charge is equivalent to that current, right? If you have a current, it's moving, and because of that, that creates magnetic fields, right? That's obviously what Aston found, right? However, now stay with me here. So the direction obviously of that magnetic field is perpendicular, right? It's perpendicular to that current that's being produced, right? So now when a charge oscillates, when, let's say, it's moving, right? Kind of like, say, if you just created like AC current, it's oscillating, right? When you move in oscillation, that's still moving of an electric field. you have like, for example, electron moving, say, in an antenna, for example, because that, releases electromagnetic radiation, right? That essentially produces that electric field and magnetic field, but this time you have an interaction of the two. So you have this acceleration that causes fluctuations in that electric field, and these fluctuations of the electric field is what induces the magnetic fields, and that obviously oscillates as well. So you have an oscillation of both magnetic fields and electric fields, and this is what like the whole definition of like electromagnetic radiation, the QCAA. It's very confusing, but because you have a magnetic field which is produced, which is perpendicular to the electric field, and they're both oscillating. So they propagate and oscillate through the medium as now electromagnetic radiation. The electromagnetic radiation is an interaction between the magnetic field that the electric field induces, basically. So that's basically what you guys like. I think you guys have to kind of just try and memorize that like definition as well. But that's like the oscillating charges basically creates this oscillating electric and magnetic fields. They propagate outwards from that source at that speed of light, obviously, because of like the light. It's an electromagnetic radiation speed of light. And that's what you call the electromagnetic wave, basically. So those are the two things that you probably should like memorize as well. So yeah. Um, yeah, and obviously that's what creates that electromagnetic spectrum that we see, and obviously visible light's part of that. So that is basically a very brief summary of it. Last thing I wanted to cover, these look very confusing, but these are basically Maxwell's laws. So remember after I mentioned, sorry, let me just quickly check the chat because I saw a question. And the charge needs to be positive 1C. So if you're talking about, sorry, if this is the question to do with like the electromagnetic radiation, it's just a charge that like creates an electric field or a magnetic field. So obviously, generally, say if you have like a microwave or like if you have an antenna, that would just be electrons basically moving, right? So but yeah. Yes, delta means change in, and then you have flux, which is the like this. I think I forgot what the Greek letter is, but that's flux, the Greek letter, phi, I think it is. And then the delta, which is a triangle, just means change in, so which means change in flux. Sorry, I read something in my Oxford textbook, and I thought it said that the charge needed to be positive 1C to produce the magnetic field. Uh, so I mean, if you talk about a current carrying wire, there's electrons in it, which is obviously a negative charge, and that produces a magnetic field. But yeah, so it definitely doesn't have to be, and I'm assuming the positive one, like that's a specific, uh, oh, okay, awesome. Okay, awesome. Okay, cool. Um, what are P and epsilon in the first equation? Okay, so yeah, no, okay. So yeah, with these Maxwell's equations, these like are very confusing with like what each of these means. So don't look at those things. Because but they mean something that we've covered like today. For example, this is just a very fancy way of talking about like the electricity, like the electric field that we've talked about, right? So electric field is proportional to the electric charge. That is all what that first equation is saying. Trust me, you don't need to know any of these. I don't even know that what the each of the like the variables mean. But this is just again outside the scope of your thing, but I just thought that this is a very nice way of like summarizing kind of thing, right? So next one is basically the magnetism. So it's like, magnetic field, what we talked about, like, how magnetic field is, formed basically, right? Third and fourth are kind of like the more important ones that we've been talking about. So the third one is the Faraday's law of induction, basically. So where you have that changing magnetic field and that creates an EMF, right? And then last one is the Ampere's law, which we talked about at the start. But this is slightly different because you have a Maxwell's addition to this as well. So he's kind of like changed it up a bit. But it's basically where like the magnetic field is proportional to the current density. So that we kind of briefly talked about, but he's added a little bit more. But that is a very like somewhat of a good summary. in terms of Maxwell's equations. He's the one who kind of put everything together. So at the end, okay, that's basically all I had. But I'll answer the questions that were in the the slider. Where's the slider? Okay, cool. So there was one question about. Sorry, it's just loading currently. Okay. What are some tips to get 100 in physics? Okay. So tips. Okay. I think this is the biggest like kind of pothole people get into is please do not answer questions like at the start when you're learning. Do not learn by like practice questions. I know it's a bit like weird to say that because at the end, closer to external exams, 100% only do practice questions, but do not learn through practice questions because then you're only learning the formulas. You have no idea what the formulas mean. You don't know the theory behind it, right? So please do not just learn about formulas. Okay. So do not learn just the formulas and do not just think about it just substituting in formulas. So that's like my first tip. Second tip is I cannot stress this enough, but I don't know if it's useful to everybody here, but I found that relating to the real life application is so important, right? Um, especially with the electric field stuff. My dad is the one who taught me a lot of it, and he's a structural engineer, but he works in an electrical engineering company. So everybody he works with is electrical engineers. So they basically like they do transformers like in and out like every day, right? So like that's kind of like the real life application that I like really like kind of value in that case, right? And it's really helpful in learning physics, especially. Obviously chemistry a little bit less, it's a bit more theory based, but like that's like another tip. Third tip, obviously closer to external exams, practice questions, spam practice questions. Um, the other thing is don't forget about the physics that you did in like grade 11 apart from like sound and like light and that stuff, but like the force stuff specifically, like applied force, frictional force, all those forces, normal force. Keep that in mind because you guys can look at the 2021 external exam, which is the one I did, but there was a question on that like brought in tension, I'm pretty sure. So tension, as far as I knew, is not in unit 3. So I think that was like unit 1 or 2. So keep on top of your force stuff. And obviously keep on like review as well. Like reviewing your content as well. So do not leave it to the last minute to learn that because then obviously you will start really needing to like Anki basically. Um, wait, hold on. There's a lot of questions. Momentum. Uh, moment. So looks. What is funny? Okay, no, okay, cool. So it's all good. So yeah, so that's what I would recommend in terms of that. Um, Obviously, Unit 4 is a completely kind of different story. So hopefully I can tell you guys about that later on. But yeah, I hopefully can get a bit more like advice slash tips in the next one. I'll definitely get you guys some tips, the stuff that I did. But yeah, understanding is key. And just for reference, like obviously I'm not saying that you guys should do this, but I never wrote notes at all in year 12. I never wrote notes. So it's all about like it's not about content recall. It's not about like, content regurgitation in this case. It's very about like understanding. And the thing with understanding is like you will never like you will never need to remember it, if that makes sense. Like in the like external exam, when you blank out, you shouldn't like lose that knowledge because you're not remembering it, right? Blanking out is always relevant to like knowledge, like memory stuff. So okay. Is Unit 4 physics hard? Honestly, I loved Unit 4 physics. I'm not gonna lie. I loved like especially Einstein's like theories of special relativity. They were really interesting. Um, but yes, I would say it is hard. To understand. But I think they would give you the harder questions from Unit 3 because they can like it's much easier to give you harder questions from there, if that makes sense. It's very hard because even like QCAA doesn't know much of like modern physics, like about quantum theory and like stuff. So they can give you like for example, special relativity, they'll just maximum give you like, something moving at like speed of light, figure out the time that they like, yeah, exactly. Unit 4's all theory, exactly. They can basically like only like give you some like Lorentz like, the Lorentz like factor thing, like the formula related to that. So it's question wise, it is I would say easier, but the content itself is obviously much harder. What is Laplace's law? Yeah, that's a good question. What is Laplace's law? I'm not sure if that's something specific that I needed to know, but sorry, I can't answer that. Have you started your MD at Griffith? Yes, I have, my first year. So I finished my undergrad last year, and I've started my first year at MD at Griffith Gold Coast. Did planetary stuff come on your external exam? Generally planetary stuff. I don't remember exactly like my specific external exam if it came on, but because like you guys can definitely like just look up my external exam on like QCAA and see if it did. But if they give you planetary stuff, it would be about like similar to what they give in a data test. They would give you like this against this and then figure out mathematical relationship stuff like that. So um that is a really good tip. Yeah. So yeah, before your mock and external, get a group of friends together and spend time going through the syllabus and thinking of how. That is awesome. Yeah, I would 100% recommend that. Yeah, yeah, there you go. Yeah, exactly. So it's yeah, it was comparative analysis exactly. So those are the type like where how you would get like planetary stuff because it is like obviously relatively easy stuff. Like the orbital stuff and stuff like that. Do you recommend ATAR notes? I didn't use ATAR notes, so I can't really recommend it, honestly. Um, yeah, sorry about that. But yeah, I don't know much about ATAR notes and whether if it's good. But apart from that, it seems that those are all the questions. I will get you guys some tips. Do you recommend tutoring? Yes, I do recommend tutoring services at ATAR Saver, 100%. Um, I'm from ATAR Saver, so yes, 100% recommend tutoring at ATAR Saver. We do have like a program that will cover like this like time of learning from physics every week. So rather than like obviously one master class that kind of covers like 20 hours of like content in like 1.5 hours. So yeah, but I'll let you guys know when that comes out. So yeah, does it save your ATAR? Oh, you bet it does. Yeah, definitely saves your ATAR. Yeah, 100%. At least your physics score, hopefully. Yes, thank you, Sam. That's appreciate it. I genuinely would have forgotten to plug in. Yeah, okay, awesome. Otherwise, yeah, if you guys for which subjects? I'm assuming if this is related to the ATA Saver program, we do methods and physics. We're planning on like we're like in the last phase of like developing it. So yeah, physics and methods is what we're planning on. And we've planned it on official live mock exams as well. So like you guys will come to like one of the centers that we probably will set up and then like at UQ or Griffith or something like that. And then like you guys can do official kind of like mock exams, like much more like much better than the ones you do at school, hopefully. So um how did you do regular review? Oh, okay. I'm actually really bad for this question. I'm sorry. I did not do. Okay, I'm not doing what I preach here, but I did not do regular review, which is why I'm telling you guys to do regular review. Because I didn't do it, and I had to kind of like spam study at the end and like understanding. Okay, to be fair, electromagnetism and stuff like that, I did at that time. I learned it properly then because I was like asking my dad. I'm like, surely you know about transformers. So I asked him then, and then yeah. Cramming is I'm not gonna lie. I'm not gonna say it's not the good because that's all I do. But uh yeah, okay. Well, yeah, but I don't recommend cramming, but I guess yeah, you're right. Like a lot of the high scores like do come from cramming. So but I do recommend 100% staying on top of your content though. It is kind of like annoying at the end, unless you're very good at timetabling. And the other thing is that like in 2021, they didn't have any like accelerating classes. So, if you have all 6 subjects, then you really need to like schedule your time, really well. Or you stay on top of your content throughout. Because the thing is, when you guys are doing your IA2 and IA3, you forget about content like on the whole, in that period of time. So definitely keeping up on top of your content. But yeah, stay consistent with all of the topics, and hopefully I'll be doing a unit 4 one whenever I can. Like special relativity and quantum. Those are super interesting. Especially like wave particle duality of light. That is like incredibly confusing, but also super interesting. So yeah, awesome. Can't wait. Yes, I'll try to do one for unit 4. Hope you guys like find it useful though. And like apologies as well again because I came back from a flight like yesterday. So this was kind of rushed. Hopefully I can do a better job next time. But hopefully you guys got something out of it at least, from the 1.5 hours. So um yeah, awesome. Otherwise then yeah, good luck for the remainder of your IA2. Let me know if you guys ever have any questions, just like ping me. But I guess please don't spam it. But I'll try to look at any questions when you can. So when I can. So yeah, awesome. Thank you guys for attending. Really appreciate you guys. It shows that you are interested in actually doing well. So awesome. All right, I'll end this call. See you guys. Bye. Thank you. Good.